graphene-based terahertz patch antennas. This is a review presentation in which we will be discussing the basics of graphene and also its application in the field of terahertz patch antennas. Graphene is a single atomic layer of graphite, and as we can see, this is the graphite, and if we peel off its single atomic layer, the graphene is a 2D material which looks like this. This graphene is having a single layer of carbon atoms which are arranged in the 2D honeycomb lattice structure. If we roll this graphene material into a shape of a ball, another nanomaterial forms, that is fullerene. If we roll this same graphene sheet into a form of tube, then another nanomaterial forms, which is a 1D material, carbon nanotube. And if we stack together all these graphene sheets on top of each other, then a 3D material forms, that is graphite. In graphene, as we know, in any carbon atom, there are 4 valence electrons. 3 of them are sp2 hybridized and form these sp2 hybridized orbitals. And one of the leftover electron forms this pz orbital, which is perpendicular to the plane of this sheet. These sp2 hybridized orbitals form sigma bond with their adjacent carbon atoms, and the pz orbital forms pi bond with the pz orbital of their adjacent carbon atom. Now this is how it looks after these bondings. These are the sigma bonds between the carbon atoms, and these are the pi bonds between the pz orbital of the carbon atoms. Now the property of graphene is actually decided by these bonds. These pi bonds are responsible for very high thermal and electrical conductivity in graphene. Also, these sigma bonds are responsible for very high mechanical strength in graphene. This is the energy band diagram of graphene, where we can see here that valence band and conduction band touches each other at a point which is called direct point. Also, here the band gap is 0, and if this graphene is intrinsic, then its Fermi level will lie at this direct point. The EK relation is having a linear relationship where E is directly proportional to K, and this proportionality constant actually depends on the Vf. Vf is nothing but a Fermi velocity, and here this value of this Fermi velocity is 1 by 300 times of the speed of light, which is very high. Normally in other materials, the velocity with which electrons can travel is very low, but in case of graphene, since the electrons behave like a relativistic particle, its velocity is almost reaches to the speed of light. Graphene, if we try to compare it with other materials, this is the band structure, band diagram of insulator, where the band gap is quite high, greater than 3 electron volts. This is the band structure of a semiconductor, in which band gap is not that high but not that low too. That is, let's say take an example of silicon. The band gap is around 1.1 electron volt. This is the band diagram of a metal in which valence band and conduction band overlap with each other, and this is the energy band diagram of graphene, which is called semi-metal, where the band gap is 0 and the valence and conduction band touches each other at a point called direct point. Now Now here graphene can be doped in two ways. We can dope it with electron also, we can dope it with hole also. Now suppose this is the energy band diagram of intrinsic graphene, in which we have not doped it with any one of the charge carriers like electron or holes, and when we dope it with electrons, this Fermi level move upwards and it reaches it gets into the conduction band, and then this graphene is called n-doped graphene. Also, we can dope it with holes. In that case, the Fermi level will move into the valence band, and the band diagram will look something like this. Here the Fermi level is also called chemical potential of graphene. Suppose if we move the Fermi level either up or down, the chemical potential of graphene is changing. The doping can be done in two ways. First one is chemical doping, another one is electrical doping. Chemical doping, we all are aware about it. The way we do the doping in normal semiconductors, but electrical doping is the unique property which graphene is having as compared to other materials. So in electrical doping, for doing electrical doping, we dope the graphene layer with either electron or holes electrically by applying an electrical bias to the material, perpendicular electrical bias to the material. So for that we need to first fabricate a device of graphene. Here this is the simple MOS kind of structure in which we have a silicon. Over that we grow a layer of silicon dioxide. Over that we transfer graphene layer, and we form two electrodes. So this electrode is acting like a source, this electrode will act like a drain, and this electrode will act like a gate. So this is a simple MOSFET kind of structure, device structure. And here for electrical doping we need to apply a perpendicular electric field to this graphene layer. So for that we will be using this gate voltage to apply a perpendicular electric field to it. Now this is the band diagram of intrinsic graphene. So in this case, since the Fermi level is lying at the center, so that is why the charge carrier density is very low. Since this is the relationship between the conductivity and charge carrier density, so conductivity depends on charge carrier density as well as mobility. Mobility itself is very high in case of graphene, but charge carrier density we can vary. In case of intrinsic graphene, charge carrier density would be very low. So that is why for this case the conductivity is very low, and hence the resistivity would be very high. So this is the relationship between the resistivity and gate voltage. So if gate voltage is 0, it means we have not doped it with any one of the charge carriers, then the resistivity would be very high. This red dot is showing us the present resistivity. Now when we apply a positive voltage to this gate, then what happens is, since here the positive voltage has been applied, positive charges will be on the silicon plate, and negative charges will get induced on this layer, or you can say on graphene. So this induced negative charges will dope the graphene layer with electrons, which will lead to shift this Fermi level into the conduction band, and it will dope this graphene layer with electrons. Also, because of this, the resistivity will fall down to lower value, or you can see the conductivity will increase to higher value. Now if this is N doping in graphene. Now suppose if I change the gate voltage to 0 again, Fermi level is at the center and resistivity is again 0. Now I apply a negative voltage to the gate. Now what happens is that at the silicon plate we have negative charges, and on the graphene layer we have induced positive charges. Because of this induced positive charges, graphene gets doped with holes that will lead to move the Fermi level down into the valence band, and this will lead to again increase the conductivity and hence decrease the resistivity to a lower level. So this is the way this electrical doping can be done in case of graphene. This property is actually called ambipolar field effect in graphene. Why ambipolar? Because it can be doped in both ways, with electron also, with dope also, with hole also, and we can say that we can dope it to p-type also or to n-type also. So this is a very unique property in graphene which we don't really get in other materials. So let us discuss all the unique properties of graphene. It is having a very high carrier mobility. It is around 2 into 10 to the power 5 centimeter square per volt second, which is very high. In case of copper, we have carrier mobility of around 30 to 50 centimeter square per volt second. So as compared to copper or other metals, the carrier mobility in case of graphene is very high. It is having a very high mechanical strength. It is 200 times stronger than steel. It is having high thermal conductivity. Also, it is highly flexible. So if we want to fabricate flexible devices using graphene, so it will be quite easy to use graphene for flexible devices. So there are various techniques to synthesize graphene. Mechanical exfoliation is one way. Chemical exfoliation, CVD method, epitaxial method. These first two methods, mechanical exfoliation and chemical exfoliation, produces small area graphene. Area would be in the range of few microns. So that is why it is suitable for dispersion in polymers for polymer composite films. The places where we want to fabricate devices from composite materials, then in those kind of devices we can use these graphene. The CVD graphene produces very large area graphene. So we can produce it with the area in the range of centimeters or inches also. So that is why it is suitable for technological applications like FETs, interconnects, antennas, etc. Mechanical exfoliation is the simplest method with which we can synthesize graphene. In this, we use a scotch tape for peeling off a single atomic layer of graphite. So here this is the graphite. Now we stick a tape called scotch tape on top of this, and we peel off few layers of graphene. When we peel it off, few layers of graphene comes out with the tape. Now what we do is we paste another tape on this peeled off graphite layers, and then we again peel off few layers out of it. So when we keep on doing this, what happens is that there is a stage comes when single atomic layer is left over on the tape. So that single atomic layer of graphite can be transferred onto the required substrate. Suppose I want to transfer it on SiO2 substrate, then I'll just paste that tape onto the substrate and peel off the tape. So the single atomic layer will get transferred over here. So this is the optical image of the transferred graphene. So as we can see, there are layers of different colors, and this lighter one is actually the monolayer graphene. This one is the a little bit darker one is actually the few layer graphene, and we can characterize the number of layers which are present by using Raman spectroscopy. Another method which can give us large area graphene is CVD method, which is very popular because most of the devices which has been fabricated is by CVD graphene. Now here CVD graphene gives us a very large area graphenes, so that is why it is very popular. So for that, for synthesizing CVD graphene, we just place a thin metal sheet into a furnace, and the furnace is heated at around 750 to 1200 degrees Celsius, and then we supply a methane gas into the chamber. There is a reaction between this methane gas and the surface of the graphene, surface of the metal, and graphene layer grows onto the surface of that metal. This metal can be copper or nickel. So once it grows, we need to cool down this furnace at a very high rate so that multiple layers of graphene doesn't forms. So this is the way we can synthesize graphene by CVD method. But the problem is that we can synthesize it on metallic sheets only, like copper or nickel. We need to transfer it to the required substrate, and that transfer process is another problem which we face. But these days many methods has been researched so far, which makes this transfer process quite easy. Another method of graphene synthesis is liquid phase exfoliation, in which first method, there are kind of three methods. First method is we the basic material which we start from is graphite. We take graphite and then initially we oxidize it. Oxidation process it induces a kind of oxidation into this graphite sheets, because of which the oxide groups gets in between the sheets and separate out these sheets. Then when we try to ultrasonicate it, those sheets get separated. So now this is the sheet after oxidation and ultrasonication, and this sheet is a single atomic layer of graphene oxide, and to get graphene out of it we need to reduce it to graphene. So we when we do the reduction, we get the single atomic layer of graphene. So this is one way of synthesizing graphene by liquid phase exfoliation method. Another way is we take graphite and we put it into some solution and we ultrasonicate it. When we ultrasonicate it, due to very high frequency vibrations, those the sheets of graphene separate out from graphite and forms graphene. But this breaks down the graphene sheets into even smaller area, so that is why it leads to very small area graphene. Now the method to characterize graphene is the most basic method is Raman spectra. So we do the Raman spectroscopy of graphene, in which there are three major bands which we get. This is our 2D band, which we get around 2600. This is the G band, which we get around 1600, and this is the D band, which we get around 1350. So these three bands tells us the quality of graphene. This D band actually tells us the defect present in the graphene. So if this D band intensity is high, it means that more defect are present in the graphene sheet. Now to analyze the number of layers of graphene, we use this method, which says that if the intensity of 2D peak and G peak is greater than 2, then it is a single layer graphene. And if the intensity of 2D peak and G peak is between 1 and 2, it is a bilayer graphene. And if this intensity ratio is smaller than 1, it is a few layer graphene. This is the very basic method to characterize the quality of our graphene. There are many other methods also, but this is the most basic method to analyze whether we are having single layer of graphene, bilayer of graphene, or few layer of graphene. This is the comparative study of Raman spectra of single and few layer CVD graphene. Here we can see this is in this case the intensity ratio of 2D and G peak is greater than 2, so that is why it is a single layer graphene. And here the intensity ratio is almost smaller than 1. Here 2D peak is smaller than G peak, so that is why it is a few layer graphene. In the electromagnetic spectrum, terahertz gap lies between the microwave frequency range and the infrared frequency range. It is called terahertz gap because at present the technology for generating and detecting the electromagnetic waves in this terahertz range is still underdeveloped. Below this terahertz gap means the radio frequencies and micro frequencies. The electronic devices are well developed for generation and detection of the electromagnetic waves of these frequencies. And as we go to higher frequencies than this terahertz gap, the photonic devices like lasers and photodetectors are also well developed uh, for generating and detecting these higher frequencies. But this gap is still underdeveloped because both the electronic devices and photonic devices are not able to reach this frequency to develop the technologies to generate and detect the frequencies of this range. So that is why this range of frequencies has been given the name terahertz gap. The frequency range goes from zero point 0.1 terahertz to 10 terahertz in this range, and if we talk in terms of wavelength, it goes from 3 mm to 30 micrometer. So that is why it is very important to focus on development of technologies for generating and detecting this electromagnetic spectrum. Also, this electromagnetic spectrum is having a lot of application in the field of astronomy, high-speed data communication, medical imaging, quality assurance, security screening, and so on. So that is why it's very important to develop technologies to detect and generate the electromagnetic spectrum in this range. So this is the basic structure of microstrip patch antenna. As we know, when we talk about data communication, antenna is a very basic device which is required. Uh, for microwave communication, the patch antenna based on copper is quite famous, and it was also tried to use those designs of patch antennas in terahertz range, but there were a lot of problems which we were facing. So that is why there is a requirement to find out another way to design antenna which works in that terahertz range. So let us first just discuss a little bit about microstrip patch antenna. So this is the basic structure of the patch antenna, where this is the metallic ground plane. Over that we have a dielectric substrate, and over that we have a metallic patch. Here this is a rectangular patch, and here the length of this patch should be lambda by 2, where lambda is the resonant wavelength of this antenna. So here in this kind of antenna, there are majorly three kind of losses. First one is dielectric loss, another one is radiation loss, and third one is conductor loss. Conductor loss conductor loss also consists of three kind of losses, where first one is ohmic loss. When the resistivity of the material is high, or let's say for some reason the resistivity increases, then the ohmic losses also increases. Skin effect loss is the loss which increases when we go to higher frequencies. As we know that at higher frequencies, the skin depth of the current decreases, because of which the effective resistance in which of the metal patch also increases. So that is why the ohmic loss increases. Scattering loss actually is because of the surface roughness of the copper patch. When the roughness is quite high, and as we know, as we go to higher frequencies, due to skin effect, the current is flowing on the surface of the metal. So where the metal is quite rough, and if the skin depth matches with the roughness uh, uh, of the metal patch, then definitely scattering would be very much prominent. So which lead to lot of loss. So as we move to higher frequencies, let's say terahertz frequencies, then these copper based patch antennas, which has been designed for microwaves or radio waves, faces some problems or limitations, we can say. As we know that the length of the antenna should be lambda by 2, where lambda is the resonant frequency of this antenna. In microwave, since the frequency was from 1 to 300 gigahertz, whereas in terms of wavelength, it is from 30 centimeter to 1 mm. So in this microwave range, the length of the antenna patch used to be in the range of millimeters, which is quite high dimension. But as we move to the higher frequency, that is terahertz frequency, the frequency range is from zero point 0.1 to 10 terahertz, and wavelength is going from 3 mm to 30 micron. So here in this case, the length of the antenna would be in the range of few microns, which is very less. So due to that, we face some problems in the terahertz range. So the first problem is that as we go to the lower dimension of the patch of this antenna, the resistivity of the copper increases because of the grain boundary and line edge scattering. Also, at lower dimensions, the current density increases, which may lead to electromigration, or you can say the copper patch can get damaged if the current density increases beyond a limit. Also, at higher frequencies, skin effect increases, which also increases the effective resistance of the patch, which also leads to a lot of ohmic losses. Also, copper is always susceptible to corrosion. So, this is also one limitation of copper. Now, here we have just tried to show the skin effect as we are moving from to higher frequencies. We can see the cross sectional area in which the current is flowing is decreasing. So we can say the effective area in which current is flowing is decreasing. So if we try to calculate the AC resistance at higher frequencies. So since at higher frequencies the effective area is decreasing, so the AC resistance increases because of that. And this AC resistance actually depends on square root of the frequency, is directly proportional to the square root of the frequency, and because of this the ohmic loss is also directly proportional to square root of this frequency. This graph shows the relationship between skin depth and frequency. We can see in all these metals, gold, silver, copper, as skin depth, as frequency increases, skin depth decreases. Here we can see at 1 terahertz the skin depth of copper is around 0.65 micrometer. Usually we keep the thickness of copper as 30 micron, and if we go to the frequency of 1 terahertz, then since the skin depth is 0.06 micron, so the whole thickness goes to waste and the resistance increases to very high value, which leads to lot of losses. So that is why it is not feasible to use these copper based patch antenna at higher frequencies. Also, scattering loss in case of copper is quite high at higher frequencies, because uh, if the roughness is high, the scattering loss will also be high. If roughness will also be high, sorry. If roughness decreases, scattering loss decreases. Here you can see the scattering loss was minus 8.75 in case of high roughness, and it decreased to minus 7.25 in case of lower roughness of copper patch. Now, if we try to take an example and try to understand what exactly is happening, suppose the roughness of our average roughness of our copper patch is around 6 micrometer, and as we know, we have seen the relationship between skin depth and frequency. So from that, we found that at 1 gigahertz, skin depth is around 2.1 micrometer. So we can see, we can compare the roughness and skin depth. Skin depth is smaller than the roughness of the copper patch. So what happens is that since the current is flowing on the surface in the thickness of 2.1 micron, where the surface is totally rough, so a lot of scattering will happen, and scattering loss would be prominent. So that is why in higher frequency range, this roughness also leads to lot of scattering losses in copper. Now let us see what happens to skin effect in case of graphene. If we take graphene is actually a zero point 0.3 nanometer thick material. So the thickness of single layer of graphene is zero point 0.3 nanometer, and if we take the ratio of skin depth and thickness and try to plot it with respect to frequency, we get this kind of relationship. So here, important point is to note that the ratio of skin depth and thickness is always greater than 1. It means that skin depth is always greater than the thickness. So that is why even if we go to higher frequencies, the skin effect problem is not going to change the effective resistance of the graphene at all. So skin effect is not a problem in case of graphene. So this is one advantage of graphene over copper. Second thing is roughness. The thickness of graphene is zero point 0.3 nanometer, and uh, e- even after fabrication, the roughness increases up to 0.65 nanometer. Now what happens is that during fabrication we use lot of polymer layers on the graphene sheet, and even after removing those polymer layers, some resist residuals are left over. You can see this area is having resist residuals on the graphene sheet. So because of that resist residuals, the roughness of graphene sheet increases and reaches up to 0.65 nanometer. So here to this roughness can be uh, easily removed, and we can get a clean and smooth graphene. So the one of the process is laser cleaning. In that we use a 532 nanometer laser. This is the normal laser which we use in Raman spectroscopy, and we expose the area of graphene where we want to clean it uh, to that laser for some time. Let's take this example. Here we have exposed this area of graphene to 10 milliwatt of this laser beam, and we waited for around 700 seconds, and we found that with time this roughness is decreasing, and it has reached up to 0.15 nanometer at about 700 seconds. So it proves that the roughness, the graphene area in this region has been cleaned, and this diagram shows us the cleaned graphene sheet. This circle, inside this circle, the graphene is smooth, and outside this circle graphene is rough. So this area was exposed to this laser beam. So this is one way of cleaning graphene. Another way is this was optical cleaning, and another way is electrical cleaning. Okay, before we move to electrical cleaning, let us see what happens to the mobility of graphene after laser cleaning. So these two diagrams are before and after cleaning. This is source, this is drain, and this one is the graphene sheet over which polymer residuals are there. After cleaning this area, we can see it is totally clean. Now here, when the polymer is uh, deposited on the graphene sheet, actually the graphene sheet gets p-doped, because of which if we try to plot the relationship between gate voltage and resistance, we get this kind of graph. Here the charge neutrality point, which is the highest resistance point, has been shifted to the right hand side, or you can say positive gate voltage. If the charge neutrality point shifts to the right hand side or positive gate voltage, it means it has been it has been p doped. And if it shifts to the left hand side towards negative gate voltage, it means it has been n doped. So here this is p doped, and after cleaning this charge neutrality point shifts to the center, or near to zero gate voltage. So it means that the graphene has been cleaned well after this exposure to the laser beam. Also, these people also calculated the mobility before and after cleaning, and here we can see before cleaning the mobility was nearly around 2000 centimeter square per volt per second, but after cleaning it has reached to nearly about 4500 centimeter square per volt per second. So you can say that almost more than double. So mobility has been increased more than 2 times after cleaning. So the benefit of cleaning is not only the reduction in the roughness of the graphene sheet, but also improvement in its mobility. So here this is electrical cleaning. Um, to clean the graphene sheet electrically, we usually pass a very high carried current density through the graphene sheet. So this is actually the uh, this is the CVD graphene. This is the single layer graphene. We have chosen this area and have fabricated this device for this area of graphene, which is single layer graphene. This area is multi-layer graphene. These patches are multi-layer graphene, and this one is actually the area where graphene has been edged out. This is actually SiO2 below the graphene sheet. So we fabricated this device in which we have deposited two electrodes, anode and cathode, and we are applying a bias voltage across this graphene sheet. Now, since the CVD graphene is always polycrystalline in nature, it is having certain grain boundaries in the sheet. So what happens is that during fabrication process, these polymer chains, these polymer chains get trapped into these grain boundaries. So even after liftoff and all, it doesn't get cleaned, or it doesn't come out from those grain boundaries. And also on the surface of this graphene, these polymer chains form a, get attached and form some kind of bond with it, which leads to p-doping of this graphene sheet. So to clean it electrically, we pass a high current through it. Here, this was the experiment which was performed to get to know at what point it is getting cleaned and at what point it breaks down. So we just pass a sweeping voltage through this device. So first in the first step we have applied voltage from 0 to 0.5 volt, and we got this kind of characteristics. When we increase this sweeping voltage from 0 to 1 volt, we got this kind of characteristics, in which till 0.5 volt it was showing the same characteristics as previous one, but at 0.5 volts there was a sudden jump in the current, and then we got this characteristics. So this sudden jump is due to the cleaning of graphene, or you can say the bond which were formed between those polymer chains and the graphene sheet has been broken, and the graphene sheet has been cleaned fully. Or we can say that the polymer chains which were in the grain boundaries, trapped in the grain boundaries, has been removed fully. So after that, when we applied the sweeping voltage, we got this kind of characteristics which was showing fully ohmic behavior. But before that, it was not showing ohmic behavior. Now, just to test that at how much maximum current density it can handle, we increase this sweeping voltage till 0 to 3.5 volts, and we found that when we were increasing the sweeping voltage at around 3.3 volt, this device broke down, and after that we got this noisy signal. It means that graphene sheet has been broken beyond this point, and we calculated the current density at this point, which came out to be around 10 to the power 7 ampere per centimeter square. So which is 10 times higher than that of copper, where its maximum current density which it can handle is 10 to the power 6 ampere per centimeter square. So this higher value of which we are getting here is due to very strong covalent bonds present in the graphene. So this is the case. This is the case of CVD graphene. But if we take an ideal graphene, then this value would be much higher than this. Now here the relationship between the conductivity, AC conductivity, and frequency of graphene is something like this. Here this blue one is for mu c is equal to 0.05 electron volt. Here this mu c is the chemical potential, or you can say Fermi level. Here we have applied some perpendicular bias to this graphene sheet, so it is for this particular case. And if we increase the chemical potential to around 0.25, it will, red one is the graph. So these solid lines are actually indicating the real part of conductivity, and this dotted line or dashed lines are for the imaginary part of the conductivity. Now if we take one case, this one, or let's say we take this case where the chemical potential is around 0.5 electron volt, and we can observe that initially at lower frequencies the conductivity, real part of the conductivity was almost constant, which shows that in this region the graphene behaves as a surface resistor. And when we move to the higher frequencies at terahertz and infrared frequencies, its conductivity acquires different response. Here what happens is that its intrinsic kinetic inductance plays a role of negative real permittivity, leading to support propagation of surface plasmon polariton. Here at this particular point we can notice that real part has become smaller than the imaginary part. So at this particular point, the real part of permittivity has become negative, which leads to support the propagation of surface plasmon polariton at the interface of graphene and the dielectric layer. So that is why we can say that in terahertz range, in terahertz range, the surface plasmon polariton are supported in graphene material. So this was very unique result, because in normally in metals like in case of copper or gold or silver, this surface plasmon polariton exists at very high frequencies, that is in the optical range, uh, like invisible range we can say. But in case of graphene, these SPPs are existing at much lower frequencies. So this is very unique property of graphene, which will be useful in designing terahertz graphene based plasmonic antennas. So here this is actually the dispersion relationship of the supported transverse magnetic plasmons, and this one is the impedance of the same transverse magnetic plasmons. Here the resonance frequency can be tuned by tuning the chemical potential, and hence conductivity of graphene by applying an external voltage bias perpendicular to the sample. As we can see that if we apply a perpendicular voltage bias, and if we tune the chemical potential of graphene, the conductivity is changing. Here also the conductivity, both real and imaginary part of the conductivity are changing. So if we change the chemical potential, conductivity will change. If conductivity will change, this dispersion relation will change, will the value of the wavelength of the SPP will change, and which will result in changing the resonance frequency of that antenna designed with this material, or resonance frequency of the graphene sheet of the length dimensions corresponding to that wavelength of the SPP. So here this property leads us to design terahertz plasmonic antenna using graphene. So this is the graphene sheet on a dielectric material with length L and width W, and here we can see the relationship between the resonant frequency and the resonator length. If the length is around 1 micrometer, then the resonant frequency would be around 1.5 terahertz for W is equal to 100 micrometer. If we decrease the W, the resonating wavelength is also going to, resonating frequency is also going to decrease. So for a specific width, if we try to increase the length of this patch, then the resonating frequency is also decreasing. So here this relationship shows us that with change in the length or with increase in the length, resonant frequency would decrease. So this relationship is very important to design a graphene based antenna, uh, graphene based plasmonic antennas. So let us try to first compare it with normal metal based metal patches or plasmons which exist in metals. So here this is the comparative study of resonant frequency and antenna length of graphene and gold. Here we can see, suppose if the antenna length is around 1 micrometer, then the resonant frequency in case of graphene would be around, here in this case it is, let's say it is 4 terahertz, and for the same length, in case of gold, it would be around 3, you can say 3 or 200 terahertz. So this 200 terahertz is very very high frequency. It is going to the optical range. So here it shows us that the resonant frequency for the same antenna length or same patch length, the resonant frequency in case of graphene would be much lower than the resonant frequency of metal. So this study also shows us that the resonant frequency is inversely proportional to the effective length of the patch in case of gold, but in case of graphene it is having this relation, which shows us that the resonant frequency would be inversely proportional to the square root of the effective length of the patch. So this was this relationship is very important, and this relationship actually depends on the property of the material. Here this graph shows us that how the resonant frequency is changing if we change the chemical potential of graphene. So here if we change the chemical increase the chemical potential, then the resonant frequency is also increasing to higher frequencies. So here we have tried to few researchers tried to simulate the result of tunable resonant frequency graphene dipole antenna, and this is actually in this they have tried to first design a resonant graphene based dipole antenna, and then they have tried to tune the resonant frequency by applying a perpendicular bias voltage to this graphene sheet. So this is the basic schematic diagram of this antenna. Here this is the side view of the same device. This one is a terahertz photo mixer, which is, let's say, a source, and here this one and this one are acting like uh, two uh, two poles of this dipole antenna, and here we have this substrate is gallium arsenide, and this one is a graphene sheet. Here we have here they have used double layer graphene sheet, and in between those two layers there is a dielectric. This dielectric is Al2O3. So this is shown over here. This layer is actually graphene, Al2O3 graphene. Why we are using double layer, and in between that those layers we are using a dielectric? Because we want to apply a perpendicular electric bias to this graphene sheet, so that we can tune the resonant frequency of this antenna. So here also we are having same kind of structure. Now this is the equivalent circuit diagram of this antenna. Here this is the capacitance of this gap, and this ZC is the characteristic impedance of the TM SPP wave existing in this graphene, and here overall this Zin is indicating the input impedance of this antenna. So here we can see this at 0 electron volt, when there is no perpendicular bias to this graphene sheet, then the resonant frequency was around zero point 0.7 terahertz. Now, as we increase the chemical potential by applying a perpendicular bias to this graphene sheet, this resonant frequency has been increased to around 1 terahertz. Now, for zero point 0.1 electron volt, it has increased to around 1.4 terahertz. For 1.15 electron volts, it has been increased to around 1.6 terahertz. For zero point 0.2 electron volts, it is around 1.7 or 1.8 terahertz. So we can see we could tune the frequency, resonant frequency of this antenna from around zero point 0.7 terahertz to around 1.7 terahertz, which is quite wide. uh, we got the whole range of 1 terahertz in which we could tune the frequency of this antenna, which is very very high. So this is one advantage of using graphene and fabricating or designing a dipole antenna using this material. Also, this is the relationship between resonance radiation frequency and frequency. Here we can see that the radiation efficiency at resonance is increasing as the resonant frequency is increasing. So this is the total efficiency with 10k kilo ohm photomixer, and we can see that the total efficiency at 0 electron volt was very very less, around 0.3 percent. But as we kept on increasing the chemical potential of graphene, here the radiation efficiency also increased. So this radiation efficiency is increasing because as we increase the chemical potential, the conductivity also increases. So it is because of that reason. So this was the antenna which were designed by a few researchers and simulated, but this is not an experimental result. uh, Also, the problem in this case was that the total efficiency was quite low. So to solve this problem, and the radiation efficiency or total efficiency is low because we are using graphene, because graphene resistance, or you can say resistivity, is not surpassing the resistivity of copper or other metals in this particular case. And of course we are getting the tunability advantage in this case, but the efficiency would also always depends on the conductivity, and which is not that high in this particular case. So that is why we are not getting good efficiency in this case. Now to solve this problem, a group of researchers also fabricated a metal graphene hybrid antenna. Now here this structure is same as the previous one. This is the terahertz photomixer, which is a source, and this one is the graphene sheet of same length as the previous case. And this is a gold pad or any metallic uh, bow kind of structure we have designed with this graphene sheet adjacent to the graphene sheet, and this makes a kind of bow tie antenna. The reason for extending this radiating element, which was earlier graphene, using this metallic sheet, is to increase the radiation efficiency or total efficiency of this antenna. So here the graphene is actually used to tune the resonant frequency, but not as a main radiating element. Now, in this case, the main radiating element is this metallic sheet. This is the main radiating element, and this metal is actually used to increase the efficiency, radiation efficiency, while efficiently coupling with the graphene strips. Here, graphene is also acting as a matching network between the photomixer source and the metallic structure, which is having high radiation efficiency. So here the job of graphene is not radiating element. It is not acting like a radiating element, but a matching network as well as resonant frequency tuning element. So this was the metal graphene hybrid antenna. Here we can see at the resonance, the radiation efficiency is around 3.5 for 0 electron volt of chemical potential, and it has been increased to around 9% at zero point 0.2 electron volt. So which was earlier, if we see the previous case, at zero point 0.2 electron volt its value was 3%, but in this case its value is around 9%, which is quite high. So the problem of low efficiency has been solved in this case. Also, later on, few researchers uh, worked on MIMO graphene patch antenna. MIMO is multiple input, multiple output antenna. So here, first we'll just try to explain what it is. Uh, this one is a substrate in and over that we have this patch of graphene with which is having dimension of 5 micron by 2 micron, and here inside this substrate we have this polysilicon which will be acting like a gate electrode. So we need to apply a gate voltage so that we can tune the resonant frequency. So this will be used as a gate electrode, and we apply voltage between this and graphene sheet. So this VDC will decide the resonant frequency, and what we do is we arrange this kind of antenna in an array on a single substrate. Here this is SiSaO2 substrate, and here this is the polysilicon, and all the patches are having independent gate voltage for them. So here all the antennas can be controlled independently uh, to tune the resonant frequency or radiation pattern. So here what happens is that this antenna is a kind of Yagi Uda antenna, and here this middle patch is acting like a driven element with which our source is connected. This two patches are acting like a reflector, and 1 and 5, the extreme two patches, are acting like director. So this is a kind of Yagi Uda antenna, and here all these antennas can be controlled independently with these voltages VDC1, VDC2 and so on. Okay, let us see how it works. This array of graphene nanopatch antenna whose resonant frequency can be independently controlled. Actually what happens is that there can be two states. First one is low resistance state, another one is high resistance state. Let's say that if we go to low resistance state, our this patch is tuned to the resonant frequency. Let's say we are designing this antenna for 1 terahertz, then if I keep this patch on low resistance state, then it is tuned to the 1 terahertz frequency, otherwise not, it will be tuned to some other frequency. So similarly for this one also and all these patches. So Going to low resistance state means tuning the antenna to 1 terahertz. So that is like if um, so this gives us an advantage of having high efficiency if I design it like in this pattern in which all these patches has been arranged in an array. So this design increases the efficiency. Also, it gives us an opportunity to tune the radiation pattern by by individually selecting the DC voltages, all these DC voltages. Now, suppose if I keep element 1, 3 and 4 in low resistance state, means 1, 3 and 4. This is the driven element, this one is a director and this one is a reflector. So what will happen, since this is a director and this one is a reflector, so the whole pattern of this radiation should go into the left side. So this is the pattern of this case. We can see the whole pattern is going on the left hand side. Now let's take another case in which the element 1, 3 and 5 are in low resistance state. 1, 3 and 5 means the driven element and both the directors. So since both the directors are in low resistance state means it active. Active means tuned to the resonant frequency. So since both the directors are active, so it should have a symmetric radiation pattern. So that is why we are getting this kind of radiation pattern. Now third case is 2, 3 and 5 are in low resistance state. 2, 3 and 5 driven element, the reflector on the left hand side but director on the right hand side. So since the director of the right hand side is active and reflector of left hand side is active, the whole radiation pattern should go into the left hand side. So here we can see we have got an opportunity to tune both the things. First one is the resonant frequencies by controlling the gate voltage. Second one is the radiation pattern by controlling uh, the number of patches, uh, putting it in low resistance state and other ones putting it in high resistance state and so on, whatever. So here this advantage we get in this kind of antenna. So there are three advantages which we are getting. First thing, we can design a very compact antenna. Second thing, we can have very high efficiency. And third thing is reconfigurable resonant frequency as well as radiation pattern. So this is also a simulated result, not experimental one, but this seems to be quite advantageous to design this kind of antennas, because this is solving all our problems like efficiency or the dimensions, the tunability and all. So that is why this kind of antenna seems to be quite popular. So that's it about terahertz graphene based terahertz antenna. Hope you like this presentation, review presentation. Thank you very much.